Okay, our job now is to determine the flux generated through a rectangular loop. And here's our rectangular loop. It's next to a wire, and the current is going in this direction. But the current varies, IT equals CT squared. So that's a current versus time, and it's equal to CT squared. So what that means is this wire here is causing magnetic field inside this rectangular wire to change through time. So since flux is changing, we do expect some sort of electric field to be generated, meaning that there is voltage. So we're going to start with our definition of magnetic flux. Magnetic flux, of course, is equal to the integral of B dot dA. And we'll need to substitute in just to find that flux, and then we'll figure out how it's changing. Okay, well, first of all, let's look at dA. dA, of course, so we'll use this variable here, we'll call this the x direction. So if we take an infinitesimal displacement in the x direction, that's going to be dx. And then, of course, our length here is length L. So our dA is going to be equal to L dx. So that's our derivative of the area. Now, what's our problem with magnetic field? Well, magnetic field, of course, is going to be generated by this wire, but it's going to be changing through time since current is a function of time. Well, it's a magnetic field generated by a wire, so we can say the magnetic field B is equal to mu naught I divided by 2 pi x. So now we made it as a function of x, which is also what our differential is in. So now we can combine those two. Our magnetic flux is then going to equal the integral from A to B of mu naught I divided by 2 pi x, and this is of course going to be multiplied by L dx. So once again, we've done a substitution, so we've only got one variable to integrate. So let's go ahead and do that. Let's get all of our constants outside so that we can see what we're dealing with. So we have a mu naught, we have an I divided by a 2 pi, and then what else do we have? We have L, and that we can put that there. And our variable then, we'll integrate this from A to B, is just going to be dx over x. And of course, we know the integral of that is just going to be the natural logarithm. So let's get that placed over here. So now we have a mu naught I divided by 2 pi, and let's put our L here. We're going to multiply this by the definite integral of the natural log of x from A to B. So what does that equal then? So we have a mu naught I divided by 2 pi multiplied by L times the natural logarithm of B divided by A. So that's our flux total caused by this wire. Now we have to deal with the fact that current I is a function of time t. So we know current t equals CT squared. So what we need to do now is take the derivative of this expression here with respect to time. So I'm going to go d dt. So, but inside I'm going to be taking the derivative of current with respect to time. So di dt is going to replace what current is here. So what is di dt? We're going to take that of CT squared. And of course, that's a simple power rule. So we know that di dt is going to equal 2 CT. I'm going to plug 2 CT originally where I have my I because I've taken the derivative of that. And our equation then becomes 2 mu naught CT L divided by 2 pi multiplied by the natural log of B divided by A. And of course, we can simplify this by dividing out our 2's. And we have mu naught CTL divided by pi times the natural log of B over A. And that's going to equal the value of our E, or our voltage, for this system.